All right, so today we've got a really incredible engineering detective story for you. We're talking about the mission to tame the absolutely immense forces that are just raging inside one of the world's most powerful rocket boosters, the Ariane 5. I mean, this is a story of some brilliant physics, super meticulous testing, and really, how do you control an explosion that's just barely contained? So, yeah, let's get right into it.
I mean, that's really the question, isn't it? Because think about it. When you light up a solid rocket booster, you're not just, launching something. You are unleashing a just staggering amount of energy. So the real trick isn't just making it go up. The real challenge is stopping it from shaking itself completely to pieces on the way. So yeah, that brings us to the heart of the problem here, the rocket's violent shake. The very thing that makes the Ariane 5 so powerful, its boosters, could also be its biggest weakness. We're talking about some seriously dangerous vibrations that absolutely had to be figured out and brought under control.
Okay, so here's the deal. The Ariane 5's boosters are just enormous. We're talking 3 meters wide. They're so big, in fact, that they have to be built in pieces, in these segments. You can kind of think of them as being stacked together like gigantic cans. And right there, at the joints where these pieces meet, well, that's where all the trouble starts. And this problem has a name, of course. It's called pressure oscillation. The easiest way to think about it is like a really, really powerful sound wave, a deep hum that's echoing around inside the rocket motor as it's firing. Now, if that hum gets too loud, if those pressure waves start building on each other, the vibrations can get so violent they could literally, and I mean literally, tear the rocket apart in the middle of its flight. No joke. So, in our detective story, who's the main suspect? What's the culprit? Well, the engineers had a pretty good idea. It was something called vortex shedding. It's this really tricky little phenomenon in fluid dynamics. Okay, so remember those segments we talked about? Well, to stop the joints from just burning up, they're protected by these rubber things called inhibitors. The thing is, these inhibitors, they stick out just a little bit into the main chamber, and that creates these little obstacles, these bumps, in what is basically a superheated, high-speed river of fire that's blasting down the center of the rocket. And when that crazy fast gas whips past those little bumps at the inhibitors, you get this thing called vortex shedding. You know what it's like? It's just like the wind whistling past a huge skyscraper. As the wind hits the building, you get these swirling little eddies, or vortices, that peel off one side and then the other, back and forth. And that creates this rhythmic, vibrating force. Now just imagine that skyscraper is tiny, and it's inside a rocket. And the wind is a 6,000-degree flow of burning gas. That is what's causing the shake. So, okay, they've got their prime suspect. What now? Well, this leads us to the engineering investigation plan. The teams at the European Space Agency and their partners, they put together this incredibly detailed plan. See, they weren't just looking for a quick fix. They were determined to understand this thing from the ground up. And this is actually a flowchart from the real research paper, and it shows you just how methodical they were. I mean, look at this. They planned to hit the problem from literally every angle. They had their theoretical models, right? Then they had these small-scale cold flow tests and even smaller live firings. The main takeaway here is that there was zero guesswork involved. They were building their case, piece by piece, step by step, long before they even thought about firing up a full-size booster. Which brings us to the next phase, solving it in miniature. And this was absolutely the key. I mean, you're not going to light up a multi-million-dollar full-scale rocket motor on a hunch, right? No way. First, you gather your clues, and you test your theories on much smaller, cleverly designed models. And here's a look at what some of those miniature tests involved. So over on the left, you've got the setup for what they called cold flow tests. They basically just blew air through a 1/15th scale model. This was super clever because it let them study just the fluid dynamics, how the air was moving without having to deal with, fire and explosions. Then, once they had that data, they moved to the next step, which you see on the right, subscale firings. This is where they added real combustion into the mix to see how that changed things. It was just this really smart, careful process of adding one piece of the puzzle at a time. And of course, all that hard work, all the theory, all the small-scale tests, it was all leading up to this, the full-scale firing. This was the climax of the whole investigation. Time to put the real deal on the test stand and light it up. So in 1993, it was basically the final exam. They conducted 2 full-scale booster firings. They codenamed them B1 and M1. This was it, the moment of truth. All their predictions, all their models, were they right or were they wrong? So what happened? An absolutely spectacular success. The data came back, and the maximum pressure spike from all those vibrations was less than 0.5% of the motor's total pressure. I mean, that is tiny, incredibly stable, and way inside all the safety margins. They had done it. The beast was tamed.
But wait, how did they really know it was safe? And more importantly, how did they know their theory was actually correct? Because for an engineer, it's never enough to just know that something worked. You have to be able to prove with data why it worked. You've got to show that what happened in the real world matched your predictions perfectly. Okay, so check this out. This is the first piece of the puzzle. This chart here is from that B1 motor test, and it shows how intense the pressure vibrations were over the course of the burn. And look, just like their models said they would, the oscillations really only popped up in one specific time window, between about 60 and 100 seconds. This was huge. It proved their timing predictions were dead on. And this chart, okay, this right here is the smoking gun. This is the final piece of evidence. It's plotting something called the Struhel number, which you can basically think of as a unique fingerprint for vortex shedding. Now, their whole theory predicted that if vortex shedding was the real cause, this number should stay almost perfectly constant while the shaking was happening. And would you look at that data? It is a nearly flat line, exactly where they said it would be. This was it. It confirmed, beyond any doubt, that their prime suspect, vortex shedding, was the culprit. Case closed. So, with all the data in and the theory completely confirmed, the engineering team could finally deliver its verdict. They had a stable rocket. And yeah, the final verdict was just crystal clear. First, the motor was very stable from a classical point of view. Second, they proved the pressure wiggles were in fact caused by vortex shedding, just like they predicted. Third, and this is the big one, the maximum level of those vibrations was super low, well within the safety margins. And finally, the results were the same across all the different tests, which showed it wasn't just a one-time lucky break. The design was safe, the problem was officially solved. And I love this quote from the official paper they published back in 1994. It just sums everything up perfectly. It says, "The interpretation of the experimental data is that the motor pressure oscillations behavior seems to be explained on the basis of characteristic Struhel numbers." Now, I know that sounds super dry, but that's what victory sounds like in engineering speak. It's this beautifully understated way of saying, we figured it out. The mystery is solved. You know, this whole story is really a masterclass in how to track down and tame a completely invisible force. And it really makes you wonder, right? As we keep trying to push further and further out into space, what other hidden challenges, what other weird, subtle laws of physics are just waiting out there for us? The kind of things we have to figure out before we can take that next big leap.